So let's read this question. Find the curve such that distance between the origin and the tangent at an arbitrary point is equal to distance between the origin and the normal at the same point. So we'll start off the problem by discussing the key concepts involved. Concepts involved would be distance formula, equation of tangent and normal, at a given point. And the last thing that we need is integration. Equation of a tangent at any point at any curve y equal to f of x. The equation at any point xo comma yo corresponds to the value y minus yo is equal to f dash x times x minus xo. And this is equation of tangent, or denoted by capital T, and this eqn denotes the equation. Alright, similarly we'll say that equation of normal denoted by capital N is equal to f dash of x times y minus yo plus x minus x naught is equal to 0. So this is equation of a normal at any point on the curve y equal to f of x. Usually this f dash of x corresponds to the value dy by dx. Alright. According to the problem, we'll say that equation of tangent, or denoted by t, would be y minus yo is equal to dy by dx times x minus xo. It's also called y naught and x naught respectively. Similarly, the equation of normal will be dy by dx times y minus y naught is equal to, plus में x minus x naught is equal to 0. So these are equations of tangent and normal respectively. Now the distance formula. So the distance formula is basically distance of point x1 comma y1 from y equal to mx plus c corresponds to the value y1 minus mx1 plus minus c upon under root of m square plus 1 ka modulus equal to distance. So we'll say that in our case the distance of origin from tangent distance of origin from tangent t would correspond to the value. Instead of y and x, we'll put 0 comma 0, and this y naught and x naught will remain same. So we'll have 0 minus y naught is equal to dy by dx corresponding to the value of x naught times 0 minus x naught. Now note that even though if I'm saying that f dash of x is equal to dy by dx, the point that we are considering over here is x naught y naught. So hence this f dash of x and over here would be f dash of x naught. We should also write f dash of x naught over here. Alright, so dy by f dash of x naught would be dy by dx corresponding to the value of x naught. Alright, so simply speaking, if we replace this x naught and y naught by x and y respectively, because those are points on the curve too, we can say that the distance of origin from from tangent t, this would be 0 minus y is equal to dy by dx times 0 minus x naught. We'll subtract this upon under root of the tangent slope, or m was dy by dx, so this is dy by dx whole square plus 1 इसका modulus equal to distance from origin. Alright. Similarly, distance from distance from origin, uh, distance of n from origin, distance of normal from origin would correspond to the value y times dy by dx minus x upon under root of dy by dx whole square plus 1. This modulus is equal to d n, and I'll call this as dt, our distance from origin. So hence, as these two values were equal, we can say that y dy by dx minus plus x modulus is equal to modulus of y dx minus x, y dy by dx, sorry, y minus times dy by dx. Alright, because the denominators were same, we'll just eliminate them. Alright, denominators were same. Alright, so hence we can say that our equation becomes modulus of y dy plus x dx is equal to y dx minus x dy, a modulus. Alright, so again the denominator was dx, so I just cancelled them off from both the sides. Now, because this equation is not really some standard form, I'll try to modify this as y dy plus x dx upon x square plus y square is equal to modulus of y dx minus x dy upon x square times 1 upon 1 minus 1 plus y square by x square. You can have a look now that both of these will have denominators as x square plus y square. Alright, I just divided both the sides by x square plus y square. On the LHS, we have uh, on the upside, on the numerator, we have differential of x square plus y square. So this is basically reminds me of differentiation of logarithm of under root of x square plus y square. So this is basically 1 upon under root of x square plus y square plus 1 upon 2 times under root of x square plus y square times 2x dx plus 2y dy. Alright, so this is basically 1 upon x square plus y square times x dx plus y dy. Similarly, on the RHS, it reminds of differential of tan inverse y by x. Alright, so differential of tan inverse y by x is basically 1 upon 1 plus y by x whole square times differential of y by x, which is basically x dy minus y dx upon x square. Alright, so using these two values, we'll say that this is basically differential of logarithm of under root of x square plus y square is equal to, note that because we have y dx minus x dy, we have to take a negative of that over here. So we'll have minus of differential of tan inverse y by x. Alright, and now we integrate on both sides. Integrate on both sides. Integration of d of under root of log of under root of x square plus y square is equal to integration of d of tan inverse y by x. So this means that logarithm of under root of x square plus y square is equal to tan inverse of y by x plus c, which would mean that if we take exponent on both sides, we'll have under root of x square plus y square will be equal to e to the power. There was a negative sign over here, so this is minus tan inverse of y by x plus c upside. So this is basically written as under root of x square plus y square is basically c times e to the power minus tan inverse y by x. C is some random constant. Alright. So this would be our required equation whose differential equation or rather whose distance of the tangent from the origin and distance of the normal from the origin would be same. Alright. And I hope you understood it well and best of luck.